Great. So yeah, so we're starting with number 3 on the homework from the functional equations. It's a function from integers to integers such that f of 2a plus 2f of b equals f of a plus b. Or that's not true. It's f of a plus b. Great. So any ideas where we can start? So remember, what we're looking for at the beginning is just maybe some um, maybe guessing the answer. That's one thing that's very helpful, and finding special values, or just some kind of any information. Okay. Um, yeah. So maybe what were some ideas people had?
I think uh 2x plus c would work.
Great. So let's try f of x. So this is a guess for the solution. F of x equals 2x plus c. Um, so I think actually c maybe can be 0, right? Let's see. So if I write this, 2 times 2a plus c plus twice 2b plus c equals twice 2a plus b plus c, right? And oh, it seems maybe anything can work. Yeah, okay, so that's actually for any c. Yeah, great. So probably we hope that's all the solutions. So any ideas? What any other observations from here? Mm, okay, maybe here's some meta observations. Why is this problem hard? What's difficult about this problem?
Maybe the combustion.
Sorry?
Maybe the combustion.
The composition, right? So that's right. So for me, what's sort of weird about this problem is this term here. Maybe I don't want to put that in blue, but yeah. So it's this term here that I think is sort of weird, right? Why do we like what to do with this kind of f of a plus b? Usually you need to do something clever to deal with this. So any ideas maybe what we can do? Um, so the key idea is the following. It's that if a plus b equals a prime plus b prime, right? For some integers a, b, and a prime and b prime, um, then you can actually get rid of this composition term. You can say f of 2a plus 2f of b equals f of 2a prime plus 2f of b prime. And now this, I think, at least is better to work with. And you can pick, a prime, b prime, a, b, however you want. So any ideas? So first of all, does it make sense what I would?
Yes.
So yeah, any ideas maybe with the simpler form, what can we do?
We can put together a like terms and prove that f of 2a minus f of 2a equals f of 2a prime mod 2.
Okay, great. Yeah. So f of two, so maybe all even numbers have the same parity, right? Or the function on all even numbers has the same parity. This is true. Uh, so maybe yeah. Maybe I'll give you maybe a few minutes to think about this form of the equation. There's actually a lot of this is actually very powerful form of the equation. There's a lot of information you can get from here if you figure out the right thing to plug in. So maybe I'll give 5 minutes. We're just taking 5 minutes to think about the problem.
Okay.
Okay, so let's reconvene. Any ideas or any thoughts or observations?
We can subtract f of 2a prime from the both sides and 2f of b from the both sides.
Hmm? So let's write it like this. Uh, so we write the equation maybe like this. We write f of 2a minus f of 2a prime plus 2f of b minus 2f of b prime equals 0. Okay.
And equals 2f of yeah.
Yeah. Okay, good. So then what can we do from here?
Then we I think we should first uh, no, uh, maybe I think the equation must be f of 2a minus f of 2a prime equal to f of b prime minus or 2f of b prime minus 2f of b.
Oh, like this. Okay, I see.
Yeah.
Great. Okay.
Then f of 2a minus f of 2a prime must be a multiple of 2.
Um, okay, great. Yeah, so this is yeah, good. So that's this statement here, right?
Yeah.
Okay, good.
And then f of 2a is congruent to f of 2a prime modulo 2.
Yeah, so that's okay. So that's this observation here. Very good. Um, um, so yeah, so maybe I'll make some point here, which is this form is actually very tells you a lot of information. So why is that? This is true whenever this original equation is true, right? But what is this original form? It's saying this is if yeah, so if a minus a prime equals b prime minus b, right? So if the difference in the a's equals the difference in the b's, then this thing is true, right? So um, so one thing you can do is you can say this b prime is
Um,
say, so yeah,
I tried subbing 2k so that b equals 2k and a prime equals k, b prime
b
equals k plus a.
like this.
Uh, yeah, and
Okay.
a prime equals k.
Hmm. Okay, yeah, so the difference is what? So a minus and a is a, I guess. So a minus a prime is a minus k, and b prime minus b is um yeah, so 2k plus a and 2k plus a, good. And so then what do we get? We get something like f of 2a minus f of minus 2k equals 2 times f of k plus a minus f of 2k. Okay.
I went in the first equation.
Yeah, so here you mean. Is that right?
Yeah.
And this one, okay, so you want to write it like,
Yeah, so you get f of 2a plus f of 2k equals 2 f of a plus k.
oh, I see, yeah, okay, so I wrote this wrong. Yeah, so you want f of 2a plus 2 f of 2k equals f of, but now you can cancel this one, so it just becomes 1 f of 2k equals f of now 2 f of a plus k. Okay, good, great. Good. So now,
I think we can use the first equation again to by substituting b equals 0 and a prime equals 0.
okay, so to b equals 0, a prime equals 0,
b prime equals a.
and b prime equals a. Okay, good. So now what do we get? We get, so now we'll get, f of 2a plus 2f of 0 equals f of 0. Okay, so we have f of 0 again, we can cancel. Plus f of 0 equals 2f of a. Okay, great. So yeah, so now you get a relation between f of 2a. But now I guess you can put this observation into the previous one, right? Is that right? So now what does the equation become? Okay, maybe we need some more space. So
Maybe you can define g of x equals f of x minus f of 0.
so let's so let's move this thing.
And it should satisfy Cauchy, right?
Yeah, good. So let's so sorry, I'm having some trouble with so let's do this. Move this up. Okay, great. So right, so the idea is to put the second equation to the first, or to put yeah, so you want to take this observation and put it into this observation, and together they will give us what they will say 2f of a plus 2f of k plus 2f of 0 equals 2f of a plus k. And now, yeah, so now we can erase the 2's, and it just becomes 2f of a plus 2f of k, sorry, no, not 2. Just, yeah. f of a plus f of k plus f of 0 equals f of a plus k. And now you're saying, right, so this is almost Cauchy. What do we need to do to make it Cauchy? We just need to write maybe g of x equals f of x minus f of 0. And then it becomes g of a plus g of k equals g of a plus k. Okay, and so this is Cauchy, and so, I mean, by induction, it will be a linear function. Yeah, great. So, um, what does it tell us? It tells us, so maybe we can write some more space.
I think the last question had a mistake. Had a mistake.
There's a mistake.
Maybe it's g of a plus g of b plus f of 0 equal to g of b plus k.
Uh-huh.
G of a plus g of k plus plus f of 0. G of
Uh,
a plus
so is this equation okay?
the,
I think it should be
uh,
2
I think
0.
So have I made a mistake?
And 2 of a plus k.
Oh, no, but then, I think everything, no, but everything is 2, right? So
Um,
it's like this, right? So isn't it, 2f of a plus 2f of k plus
oh,
2f of 0,
right.
right? So then I
Oh,
divide
okay.
everything by 2. I think it's okay, right?
Yes.
Yeah, so I just canceled the 2's, I think. Good, yeah. And this. Okay, so anyways, the point is what now? By induction, g of n or x equals cx for some integer c. So it tells you that f of x is equal to cx plus f of 0. And now you have to, I mean, you have to determine that c equals 2, but that's, you plug it back into the original equation. Okay, so does that make sense? Does the solution make sense for everyone?
Um, uh, I think we've made a mistake somewhere.
Oh, is there a mistake?
I think it shouldn't be minus f of 0 instead of plus f of 0.
Oh, I see. Should it be plus? Let's look.
No, I'm talking about the line just before g of x.
There's a mistake here. Hmm.
Yeah.
Yeah, you're right. There is a mistake. That's right. So actually, you're right. So it should be f of that's right. So we have f of so here we have f of 2a plus f of 0 equals 2f of a. So it should be f of 2a is 2f of a minus f of 0, and so there should be a minus. You're correct. So here it should be a minus minus 2f of 0. That's right. And then what? And then I think it's okay. Yeah. Okay.
But I didn't get how we solved that g was linear.
How we solve what?
How did we get that g is linear?
Oh, for how are you asking how we got this or how we got the second one?
Yeah.
So does it make sense how we got this?
Yes.
Okay, so from there, so then this is so Cauchy for integers, right? So how does Cauchy for integers work? We have
Oh, right. Never mind.
yeah, I mean it's basically it's just induction, right? You can say something
Yeah,
like
yeah.
g of x plus 1 uh, equals
Yeah, I
okay, okay, good. Maybe g of x plus g of 1, something like, and then it's induction, yeah. Good. Okay, any other questions? So the key idea is, it's that this for me is a very sort of weird expression. So whenever you have some composition, you either have to do something, some very clever substitution, or yeah. In this case, it's the point is this side is complicated, but there's a freedom here. It only depends on a plus b, so you can actually sort of ignore it if you correctly reinterpret. Okay, so let's go to the next question. So actually, would you guys like to talk about another one of the functional equations, or should we move to combinatorics? I'm asking, I think these problems are better if you've already thought about them. So have you spent significant time thinking about, say, number 4 and the functional equations?
yeah, I think we should do more functional equations.
Okay,
I
so we
want
can.
to try to solve the combinatorics on my own.
Okay, great. So let's okay, yeah. So let's maybe do some more functional equation. Um, so yeah, let's look at problem 4. So this is number 4. Functional equations. So let's see. So what is the problem? So here we have our function is from positive rationals to positive rationals. So and then what is the equation? So the equation is f of x squared f of y squared equals f of x squared f of y. Okay, for all x, y. Okay, so any ideas to start us off? So maybe I'll ask something. There's something strange about this. If you try to guess the solution, you can almost guess it. So what I mean is there's a solution that almost works. Do you guys know what I'm talking about?
Oh, the square root of x work.
Yeah, so if you do f of x equals x square root of x, right? Then, this, what happens? I get x squared times square root y squared is y, and then square root of that, which is equal to square root of x squared times square root of y, right? So it works but the only problem is, it's from rationals to rationals, so you can't actually use square root. So that's something a little bizarre about this problem. Um, um, okay, so any ideas? What did you guys try? What kind of, even if it didn't work, what kind of things did you try?
Replacing x and y with 1.
Yeah, great. So let's start with that. So, right. So for x and y equals 1, we get f of y, 1 rather. 1 squared is equal to f of 1 cubed. Um, f of 1 squared equals f of 1 cubed. Okay, so that's a nice relation. I don't immediately know what to do with it. So what are some other things we can try? So we can always try things like setting one of them equal to 1. So if you do x equals 1, then we get something like f of y squared equals f of 1 squared of y. Or if y equals 1, we get f of x squared times f of 1 squared equals f of x squared times f of 1. Okay. Mm, yeah, so any ideas, other things we can plug in? So one thing you can try is this whole left-hand side is very unwieldy. Yeah, this whole thing is kind of a mess. One way you can try to simplify is, okay, I see this x squared f of y squared. I can make it simpler by doing something like this. So I can say x equals 1 over f of y. Okay, so then at least the left-hand side is something a little bit more manageable. It's, what is it? Um, it's going to be f of 1 equals, um, 1 over f of y. Is that right? No, that's not quite. Have I made a
No,
mistake? No, that's not right.
I think
Yes? Uh, maybe like this rather. Mm, yeah, maybe we can rewrite this one as a f of 1 over f of y squared equals f of 1 over f of y. Okay. Yes, this is kind of a very curious looking thing. Any idea how we can use this?
Replacing y with n.
Replacing what?
With one. Y with one.
So let's put y with 1, and that will tell us immediately that, great, yes, that's a good one. So maybe, yeah, so let's create a little bit more space. Yeah, so in particular, we get that f of 1 over f of 1 squared is equal to
To one.
1, right? Good. Now what?
F of one over f of one is equal to one.
Mm-hmm. Yeah, good. So I think it's this one here, right? Yeah. Hmm. Hmm. So yeah, so in particular, right? So in particular, we also have just without the square, right? F of 1 over f of 1 is equal to 1, right? So actually now there's something we can do, right? So yeah, maybe I'll give a moment to think. So I think with this equation, actually, there's something kind of clever we can do.
Can we substitute y equals 1 over f of 1 in the initial equation?
That's right. So I think the substitution is y equals 1 over f of 1, and we go into the original equation, right? And now, so I don't have much space, so I'll erase that. And good. So what do we have now? So after doing that, we get something very nice, which tells us that so y equals 1 over f of 1, and we have something very nice, which is f of x squared, and we don't have to put anything here, equals f of x squared. Okay, so this is the first the first identity we've derived, which is something sort of nice. So what can we do with that? I think this equation has a lot of utility. Yeah, maybe I'll give a moment. We want to use this one.
I'm not sure if it helps, but I think we can prove f of y is a square for
Okay, how do we do that?
the first equation.
Mm-hmm.
I just make it f of x, f of y, and we just use the last equation. So f of x squared f of y squared equals f of x f of y all squared.
Great, yeah, so we use this red equation in the first equation to rewrite sort of part of what's making this so complicated. We rewrite it as f of x, f of y, sorry, just x, f of y, x times, sorry, what did I mean to say? Yeah, we write it
F
as
of x
f of,
times f of y.
that's right, this all squared, yeah, is like f of x squared, f of y. So, right, it's not immediately clear that this is useful, but at least it gives us something, right? What you said, which it gives us f of y is equal to f of, maybe I need more space. So it gives us at the very least, gives us this nice thing that, maybe I'll write it in red, which is f of y is equal to um, f of x, f of y squared divided by f of x squared. So it tells you that f of y is a square. Okay, good. So and y is completely arbitrary. So actually all of the outputs are squares. So that's something very curious, right? What does it mean if all of the outputs are squares? Which is, I'll say, is a square. And I'll comment since the domain, right, since the output, right, is in the rationals, being a square is like a, it means something, right? If it was like R to R, I'd say maybe being a square is not that interesting, but from Q to Q, being a square is something interesting. Okay, so I'll box this equation. Okay, yeah, so we use this equation to get that f of y is a square. If you think a little bit more, you can actually get more out of this equation. So I'll give some time to think. So, yeah, maybe we can say, maybe we can say f of x is equal to g of x squared, where g is a function from q to q, right? Okay, I think I want to start a new page because there's a lot of information here. So let's duplicate, go here. So sort of erase all of these. Right, so every output is a square, so you can say f actually comes from a function g, and it's the square of some function g, right? So now, what do we know about g? For example, if we just take the red equation, we can rewrite it as g of y squared is equal to something like g of x, g of y squared, now to the power 4, over g of x to the power 4, which simplifies to g of y squared equal, g of y is equal to g of x, g of y squared over g of y squared. Does it make sense what I've done here?
Yes.
And so what does this tell us actually?
Actually, why did we write g of y squared in the denominator instead of g of x?
Oh, that's right, x, my bad. This should be x, you're right.
Oh,
So g of y only outputs square numbers.
That's right. So g of y is also a square. But this is weird, right? Because g was defined as the square root of f, right? And so if g is outputting squares, then f is outputting fourth powers.
yeah, so by infinite descent, there should be no such function, right?
Right, so yeah, so so infinite descent is the right idea, so let's be a little bit careful. So what it's going to mean is that whatever number f outputs, it's going to be a square, it's going to be a fourth power, it's going to be an eighth power, and so on. There is one number it could output for which this is true.
1.
1, that's right. So that means it has to be 1. The output there's the only number it can output is 1. Does that make sense?
Yes.
Yeah, so the idea is, yeah, so this is sort of this identity here actually is very powerful. Since your outputs are always rationals, it just tells you by maybe by infinite descent. It tells you by infinite descent, f of y is always 1. Yeah, good. Yeah, maybe I'll make just one comment about how you would actually write the solution here. I think the proper way to write the solution is something like you can write something like okay, so we'll say something like you would prove this claim. So you say claim for any positive integer n, f of y is a 2 to the nth power. Okay, and then the proof is by induction. So yeah, so maybe we can say non-negative integer, then we can make life easy. So okay, if n equals 0, this is obvious. We're just saying it's first power, so this is clear. And then for induction, the point is f of y is, you just write this equation, and well, the point is by induction, both terms are 2 to the nth powers, which means the quotient is a 2 to the n plus 1th power. Does that make sense?
Yes.
So then it's very clear that the only number which is a 2 to the nth power for every n is 1. Okay, that's the idea. Or the only like rational number. Yeah. Good. So any questions or remarks or anything?
Would it not be enough to just say that um, G is the same as F, and hence instead of doing this whole induction thing?
Well, so but we don't know, like, you still need to show that G is always 1, right? Yeah, am I missing something, or?
No, I mean, since G is the same as F, we can also
Why is
uh,
G the
get
same as F?
another function in a sense.
Are you saying G has the same functional equation or something? Or?
Um, yeah, I mean, the last equation with G is the same as F's on the
Right.
right.
Well, so there's a difference. I mean, there's a square here versus something here.
Oh, oh yeah, I not noticed that.
Yeah, but also, even if it was the same, I mean, it's not it doesn't tell you that G and F are the same, right? It just tells you that they have similar functional equations.
Wait, but can't we just keep the F of Y in the... No, I mean, if you can take G of if you can make G of Y from mm, by taking the square root of Y, you can do the same for G, and you can always repeat this.
Mm-hmm. Uh-huh, right.
Yeah, so I mean, is induction necessary?
Uh, so you're saying rather I just say that you repeat this process infinitely, and therefore, since you can always take the square root.
Yeah.
Yeah, so I mean, you can. I'm just worried they might. I don't know. It's maybe it's a little unclear. What does it mean, this process, right? Um,
Oh,
right.
all right.
Because you have to the point is, this functional equation changes slightly, right? It's so you have to say, okay, like
Yeah, but you
uh,
can
uh,
just keep it as F of Y.
oh, I see. You're saying I can keep it like this. Um, X f of y. Yeah, but now I mean the bottom is changing, right? Maybe it's something like yeah, maybe it's G here or something. Yeah, I mean, you can, and then I guess what you need to show is something like, you need to show that in general. I still think you need to write a little bit more. You have to write, maybe you have to write something like G sub k is the yeah, I think you still need to give some kind of argument, right? So maybe
Yes.
your argument will be something like um maybe something like, you give some kind of recursive definition like G sub k of x is equal to G sub k minus 1 of x to the square root or something. And then you prove something like gk of x is always a rational number. But then I think you should do it by induction again, something like that. Does this make sense?
Yes.
Yeah. Yeah, so it's not, I mean, it's not that significant, but I think it's better to write. Here, I mean, if you want, you can write a solution and then I can look at it and I'll tell you what I think. Um, if you'd like. Uh, okay, so we've done two functional equations. I would like to do some combinatorics. So maybe I'll ask this. Were there any of the problems from, say, the warm-ups or from the first few combinatorics problems that you wanted to go over?
There were a few that I couldn't solve from extreme principle, so I Googled them.
Okay, so would you like to go over them, or we can
Um,
it's up to you. We can go over them if you would like or not.
no.
Okay, that's okay. Okay, so at the very least, I would like to go over the first problem in the combinatorics section. Yeah, I will. So what is the first problem? Okay, so maybe it'll be hard to write, so I'll just read it. You have the numbers 1 through n written in some order on the board, and you are basically you're sorting them, and you're sorting them by swapping adjacent numbers when they're out of order. And the problem is to prove that this eventually terminates. So this is something that I think, maybe you can take a lot of people take for granted, but I want to know, like, how do you actually prove this? So maybe this is,
Um,
yeah,
yeah, I think I can provide some proof.
okay, yeah.
So let's define um, E of I equals distance between i's current um, location and the i's current index and where it should be in an ordered um, after we order them.
I see. So so
So
so you're
so
saying, do
this
I? Mm-hmm.
yeah so as long as the sum of E over all I doesn't equal zero, it shouldn't be sorted, but we can put operations decrease the sum by two.
Okay, great. So we're looking at distance between
Current index and where it should be after we sort them.
I see. So is it at index I, we look at, maybe we could say this is A1, A2, AN is the number, and so like, is it the distance between AI and I, or no, so yeah, is that right? Between AI and I? Maybe it's like this.
Actually, I think there are some problems with this approach.
But do I have the correct like this notion of distance?
Yeah,
Right, so 3, 2, 5, 1, 4. So I see 3 is supposed to be in the third slot, but it's in the first slot, so that'll contribute a distance of 2. And then this, for example, is supposed to be in the fifth slot, but it's in the third slot, so it'll be a distance of 2. Okay. And now your idea is to take the sum of all of them. Maybe a capital E is like A1 minus 1. Uh, and okay, so what's the concern with this solution?
I think we could I think sometimes the uh, the sum won't decrease.
So sometimes it won't decrease, right? So what does that? So yeah, let's maybe come up with an example. Hmm, yeah, that's right. So maybe if we want to have something like,
Actually, the example you wrote before 3 and 2.
Mm-hmm. Yeah, so for 3 and 2, let's look what happens. So yeah, so what's the issue? The issue is that 2 is already where it wants to be. So when you swap them, 2 actually becomes further from where its final destination is. So 3 comes closer, but 2 becomes further. So the net difference is 0. Does that make sense? Um, yeah, so E does not always decrease. But okay, maybe I'll make some comment, which is this is the correct idea, right? So what we're looking for is some kind of so this is not called an invariant because it doesn't change, but it's called a monovariant. So we're looking for a monovariant, which means some quantity which is either always increasing or always decreasing.
I think I have another approach that should work.
Okay, so what's the approach?
For every I after it can only or after n minus 1 operations, it should be in the right after it's in n minus 1 operations, it should be in the right place.
So you're saying
Something that the number of operations has a limit.
so you're saying for every number, am I looking at every number or every index? Maybe every number, right?
Every number is
Yeah, so for every number, you're saying once it's involved in n minus 1 swaps, it must be in
at
the correct
most.
position. Or yeah, at
Yes.
most n. Yeah, I see. So how can you prove this?
Um, First of all, since it can't, uh, we can't choose the same two numbers for two operations.
Okay, great. So yeah, so maybe let's try to prove this. So the claim, yeah, so the claim is at least write. I'm just writing the claim first. So
Actually, this is all unnecessary. We can just prove that we can't use the same two numbers in two operations, and
oh,
this would be enough.
okay, great. So maybe let's let's go with that. Maybe simpler claim. So claim two numbers cannot be used in the same operation more than once. Um, and yeah, so why is that? Yeah, okay. So maybe it's something you should think about to convince yourself, but yeah, maybe Kareem, you can give me a reason.
Yeah, suppose we have A and B, such as A is greater than B.
Uh-huh.
So if B is so if B is to the left of A, they won't you can't make any operations since B won't go to the right of A.
Yeah. Maybe the opposite. If B is so B is
Uh,
bigger, right? Yeah, so maybe once B is to the right, it can't go to the left, right?
yes.
Okay, so yeah, once yeah. Okay, good. Yeah, so this is I guess something you need to convince yourself, but does it make sense, or are you guys convinced of this statement? Abdullah Karam, does it make sense what the statement is?
Uh, what are A and B?
Yeah, sure.
So A and B are two numbers, right? So for example, I guess it's something like if you start with say 3, 2, 4, 1, 5. The point is, let's say look at 3 and 2. So let's say first you swap 3 and 2, and so it becomes 2,
But
3. Yes.
I think that we can't swap the 3 and 2 because 2 is in the correct order.
So what does sorry, maybe I should clarify the question, right? So when I say correct order, I mean relative to each other. So maybe that's how I'm being, so yeah, so maybe I should have, maybe we should, maybe there's some confusion with what the problem is saying, right? So um good. So that's a good point. So let's try to understand. So the point is, if we start with 3, 2, 4, 1, 5. What I mean by the order is I mean 3 and 2 are out of order because 3 should come after 2. So what you're allowed to do is you're allowed to swap these two and become 2, 3, 4, 1, 5. Does that make sense?
Yeah, that makes sense.
Karam, does that make sense? Yeah, so what I'm saying is you can swap them when relative to each other, they are in the wrong order. So the one on the, okay, well I guess Karam is not here now. Okay, but yeah. Okay, but Abdullah, does the statement, the claim, and the proof make sense?
Yeah, absolutely.
Okay, good. Yeah. So this tells us, okay, at least it tells us the process will eventually terminate, and it gives us an upper bound for the number of steps, right? It tells us the number of steps is at most n choose 2, right? So the question is, I guess the second part is, what is the maximum number of steps? And so, yeah. So is it possible to actually require n choose 2 steps?
What was the question?
So yeah. What I'm saying is, your argument tells us that um, eventually the sorting algorithm terminates, but it also tells us um, sorting takes at most n choose 2 steps. At least if you do it this way, right? Because there's n choose 2 pairs, and each one can occur once, right? So the question is that a tight bound? Is there an initial ordering where you need exactly n choose 2 steps?
I think the ordering where they're all swapped, it's like n minus 2 and minus 3 until you get to 1.
Yeah. So I think this one will take exactly n choose 2 steps. Yeah. And maybe, yeah, so but actually here's a question. How do you prove that it takes n choose 2 steps? No matter how you sort it. Yeah, so here's actually something. It no matter how you like there's a lot of choices, right? Like which order you do the swaps in. It actually turns out no matter what order you do them in, it'll take n choose 2 swaps.
I think we can do double counting. We can just say 1 needs to move n minus 1 times, and 2 needs to move n minus 2 times, and so we get to n that needs to also move n minus 1 times, and this should be equal to 2 times n choose 2, and since each operation moves 2 of them, we should get this result.
Great. So 1 moves n minus 1 times, 2 moves n minus 2 times, and so on. So you get a total of n choose 2 steps. Sorry, maybe
Yeah.
that's not quite what I mean. No, that's not. We have to say what you have to be a little bit careful. So, right. So, okay, and then I see. So this is a little bit. Let's go to the next page. So we're saying if the initial ordering is n minus 1, n minus 2 all the way to 1. So 1 moves at least n minus 1 times. and then 2 moves at least n minus 2 times. And then it's a little weird, right? So,
Oh yeah.
no, but I think it still works.
Yeah,
Right?
I think but no, I think it shouldn't work.
It shouldn't work. Why is that?
I think I only have numbers from n minus 1 until n divided by 2.
Yeah, so you're saying it's the wrong size. So what does that mean? So it's like n times approximately, so it's approximately n times 3n over 4 divided by 2, which is 3n squared over 8, which is more than n choose 2, right? Because this is about n squared over 4. Yeah, so actually this gives you yeah, so sorry, n squared over 2, my bad. Yeah.
I think it should be less than.
Sorry?
I think it would be less than.
Yeah, here we go. Yeah, okay, so what is this argument telling us? It's telling us that it takes about at least 3n squared over 8 moves, but I guess the claim was that it always takes n choose 2 moves. So this argument isn't strong enough, right? Does it make sense?
Yeah, so now we're trying to find the bounds. Yeah.
And I mean, so the problem here is, maybe one will move to the left, and then sometimes it'll come back to the right a little bit. Like things aren't always moving towards their destination. Yeah. So what's the idea? Maybe let's think about some kind of small example, right? So
I think I have an approach now.
okay.
So we do double counting again. So for every one of the for each of the numbers we have, it should be in n minus 1 operations actually, because all the numbers on its right will have to go to its left, and all the numbers on its left will have to go to its right.
Okay, so you're saying
So we
I
get
have
n times n minus 1 divided by 2.
good. So you're saying for each number, okay, so you're saying for each number, great. So for every number, it needs to it basically needs to be a swap with every. Okay, maybe maybe I'll rephrase your argument slightly. So what you're really doing is you're looking at each pair of numbers, say I and j, and you're looking at in the initial order, are I and j in the correct order or in the wrong order? And then you're saying that the only way to correct the relative order is to have I and j be involved in a swap. So we can say it like this. What you're doing is you can think of it as double counting, but you can also think of it as what you're doing is you're counting. So let's say the original order is A1, A2, and you're counting the number of pairs I comma j such that I is less than j, but AI is greater than AJ. So you're looking at the number of pairs that are in the wrong order. And then you're saying for those numbers, for them to become in the correct order, they have to be involved in a swap at some point. Does the argument make sense?
Yes.
And so actually this works for any initial ordering, right? Like if I give you the initial ordering 3, 2, 1, 5, 4, I can just say the pairs that are out of order are so 3, 1 is out of order, 2, 1 is out of order, and then 3, 2 is out of order, and 5, 4 is out of order, right? And everything else I think is in the correct order. So 1, 2, 3, 2, 1, 2, 3, 4, 3, 5. Yeah. So this will take exactly 5 swaps to fix because each time you swap, you're fixing exactly one of the pairs. Does that make sense?
Yes.
Yeah. And so this is an example of something I was calling a monovariant, which is the number of pairs in the wrong order. Okay, and so it's a monovariant, and it's a monovariant. But so all that word monovariant means it's a quantity that either is always increasing or always decreasing. It doesn't go up and down. And in this case, it's something that always decreases by 1. So it tells you the exact number of steps for this algorithm to terminate. Does that make sense?
Yes.
Okay, great. So yeah, so let's maybe take a look at yeah, so okay, before we break, I'd like to take a look at number 2 on the combinatoric section. So but okay, so you said maybe you guys, Abdullah and Kareem, had both seen this problem before? Or maybe one of you had?
Yeah.
Okay.
Both.
Okay.
Yeah.
Okay, so maybe it would not, so would you like to go over it or do you know how to solve it already?
We both solved it.
Okay, so
Yeah.
maybe so maybe it wouldn't be so useful. Is there a problem that you would like to go over in the combinatoric section?
I didn't have the time to check them all, so I would like to go over them on my own.
I see. Okay, so you want to think about them later. I see. Abdullah, is there any that you want to go over?
The last two basically,
I
the
see.
6 and 7.
So here's what I'll say. Maybe next time, after both of you had some time to think more about these problems, we'll go over maybe one of 6 and 7 and at least some more. But yeah, so what I'll say, Abdullah, is you should keep thinking about number 6. Number 6 is and for number 6 you should think about the small n. Like any combinatorics problem, you should always think about the small cases first. And number 6, if you think about small cases, maybe you'll find some kind of pattern. But yeah, so maybe we'll go over that next time.
Okay.
Okay. Okay, so yeah, I guess is there anything else you guys want to go over? I guess we're postponing more combinatorics to until Wednesday. I'm happy to end early, but if there's anything else you'd like to do.
There's nothing for me.
Okay. Okay, so then maybe we can end early today. Yeah, so then Monday, I guess, yeah. So Monday, I guess the homework is to continue with the combinatorics problems. Yeah, so we'll do more of that on Wednesday. Okay.